Welcome to problem 13. I've only read the first question because I forget problem 13 of the last section. I have to read that up to, to be able to start on the next part. But the first one, we should find an R, and I would like simply to use problem 2 in reverse, but I think it would be a good idea to do it from the definition of the zeta function. And to get the exponential away, we must make a logarithmic derivative. And the exponential gives itself, so we must derive the interior. Oh. That was news to me. And that means if we say take the logarithmic derivative and get minus 1 divided by minus 1 minus t and expand it, it's minus the sum of t to the rth, r going from 0 to infinity, there's something strange here. When we take the logarithmic derivative, we get plus, because the minus t and the minus 1, there we go. And that is the n1 is what comes to the constant. It's all 1. And if we take 1 minus qt, so when I is 0, it becomes q to 0, it's unity. So n1 comes when it's 1. No, n1 gives t 0. This is strange. So what comes to t to the, say, first is q to the first, and that should be n2. So that doesn't really agree here. Oh, that's strange. Here we sum from r equals unity to infinity. This is what we get. So we get n1 plus n2, and here we always get, when expanding these guys, we always get unity first, not n1. So we'll need a break to check where that error is, because nr should of course be q to rth, and what I get here is q to r plus 1, I think. Well, that was easy. You can see very little time has elapsed, and that's when we take the derivative of 1 minus qt. We get, of course, minus because it's in the denominator, and then we get minus q. So up here we should have q, so it should be q, and that means that it becomes, when I is naught, it's q, and when I is 1, it's q squared, etc. And now it's totally off. Q and Q1. So this way I get plus 2. I'm sure it's from this that I'm just doing something very stupid. So it's nr t minus 1, and that means the coefficient to nr, to t to the rth, is nr plus 1. So the coefficient t to naught is n1, and the coefficient here is n2. Now we do get it. So this was just wrong. Right, so now we can go backwards the way from problem 2 to take the logarithmic derivative of the zeta function, expand it, and then we have the number of solutions, which will give exactly this. That was the first part of the problem, and for the next I'll have to read up on problem 13 and see what the situation is. I've just had lunch, and at the beginning of the lunch it occurred to me that I hadn't answered this question, that nr is equal to the norm of 1 minus alpha to the rth. According to the section, alpha is quadratic, over the rational numbers, or over z, and the norm of alpha is then 1 divided by q. That's by Wales' hypothesis. Alpha e, true alpha e is an integer. So that follows from that. Now, the norm of alpha is 1 divided by q, and that means that the conjugate of alpha is, now what is that? Their product is Q, so it's Q 1 divided by Q alpha. And that means the product of 1 minus alpha to the rth is 1 minus alpha to the rth times 1 minus q to the rth, alpha to the rth. So this q must come up here. Now that's weird. Well, let's do it and see what happens. We get unity minus alpha to rth minus 1 divided by q to the rth, alpha to the rth, plus 1 divided by q to the rth. So we should have q in the numerator, not the denominator. Couldn't it be the norm of 1 minus alpha to minus rth? No, then we would get alpha to minus r here. So I must have made some mistake with the norm. That's very weird. I think they stated in the book that the two solutions were alpha and q divided by alpha, and if that's the case, then we get the right result. And here the equation is t squared minus 2ae divided by qt plus 1 divided by q. So the product, the sum should give this, and the product 1 divided by q. Well, I got it. Alpha is the reciprocal root so the norm of the reciprocal root is q. And that means that it comes q up here, q to the rth up here, q to the rth up here, and plus q to the rth. And then we end up with the right formula. I'm back. I've had my afternoon tea, which is coffee, and I've prepared what we know. I won't be able to see as much of me as you might like. First, I've written problem 13 of section 1.9, which took a while recalling what I made there. And then I wrote down the prerequisite and what we need to prove, that fq in L to the mth is generated by the points of order L to m plus 1. And then I've added, but contains no points of exact order L m plus 2. I think we need that. And put like this, you can see that we can probably prove this by induction, as the case m equals naught is the prerequisite. So assume that we have this for some n, and then we use the proposition, the problem, where instead of q we use it on so this is giving for some m minus 1. And then we shall prove it for m, for n. So we have a point A, this is the wrong sign. I can't even write contains because it has two coordinates, but I guess you understand what I mean. Of order L to n. And then we use the problem. And it says that when we add the solutions of order I'll just write it so that L alpha equals L. Oh my God. L alpha equals A, then it's either in of order 1 or L. So that is that alpha, and I'll write the same thing. Or I believe if this is the case, this should be a Q, of course. If this is the case, then it will already this alpha has order L to nth plus 1, and that was the now I need to be careful. We just do it again. So this has order L to nth, so alpha has order n plus 1th, L to n plus 1th. And n plus 2 is n plus 1, so it doesn't contain it. And that means that this is impossible. N plus 1, that's n plus 2. So this guy is impossible. I thought that would take a little more. No, it must be an extension field, that's what it says. So that's fine, it must be an extension field. But then we have to prove that this extension field contains no points of n plus 2. Is it points of order that that we are about here? Yeah. So we have a point of order L plus 1, but we must have no point of order n plus 2. So that in that case, L squared beta, that's a beta, not a B, equals A. And then the Galois group has order L. Oh, if it contains all of the points, or rather it will contain all of the points. So if we add the coordinates of any point, then the smallest guy will contain all the points. I don't really know how many we've got, as this number squared. And the Galois group will map them among each other. And the Galois group only contains L elements. Would that be a problem? I don't know how to prove this. We should be able, from this guy, to get a point of order L contained here. Well, I need a break here. Well, it turned out to be easy. We just use this problem again with L squared instead of L. And then we get that the space generated by the solutions must either be Q to Q itself or Q to L squared. And since it can't be L squared, Q to L squared, then it must be the same space without. This is not really, I need to write it a little. So what we have here is m equals n minus 1. And then we have A lying in here. And then we make an extension. We find a guy beta and then we must put Q either to the first or to Lth, and that means that it was Q to L n minus 1, and that must be put into Rth, where R is either 1 or L squared. And L squared, that gives L to n plus 1. And that's an extension field. And so it can't already be in the smaller field here. Because if it's in the smaller field, then it must be in the original one. So that should finish the proof by induction.